it to join us today. All right. Without further ado, we were trying to figure out in Ratika's problem the number of sigma and pi bonds for a compound. Now, the textbook was a little bit confused about this. They said butadiene, comma C6H6. Now, those are two different compounds, and actually, we can't determine the number of sigma or pi bonds from either of those things alone. What we need to do first is determine what the Lewis dot structure is for that particular compound, uh, or compounds in this case, it's two different ones. And then from our Lewis dot structure, we can count the number of sigma and pi bonds. So I'm going to go ahead and draw out butadiene first. So butadiene looks like this. I know because I specialize in organic chemistry, and this is an organic molecule. And so then we have hydrogen there, double bond, another carbon, hydrogen, hydrogen. Okay, so this is the molecule butadiene. Looking at this structure, to determine the number of sigma bonds, it's going to be every first bond in between two nuclei. Sigma bonding is the lowest energy type of bonding that you can do, and therefore it is preferential to other bonding modalities. So effectively, you just count the number of bonds in between all of the atoms, the first bond specifically. So I'm going to go ahead and number them here so we can follow along. There's 1, 2, 3. Now I'm not counting this one twice because only the first bond is a sigma bond. That makes it 4, 5, 6, 7, 8, 9 for that carbon to hydrogen bond there, and 10. To me, it looks like we have 10 sigma bonds. That little symbol next to the 10 there is the lowercase letter sigma. Counting the number of pi bonds is even easier than counting the number. Oh, did I make a mistake here? I think I did. I think I counted something twice. Let me go through again. So 1 there, 2, 3, 4, 5, 6. I shouldn't have put that there. Sorry about that. That's why we label things so that we can quickly check our work. This is 6. This is 7, 8, and 9. Okay, so it is actually only 9 sigma bonds here. All right. To count the number of pi bonds is even easier than that. You're just looking for anywhere that you have more than one bond in between two nuclei. So, for example, look at this carbon to carbon bond here. The first one of them we already labeled as a sigma bond. Every subsequent bond will be a pi bond. Now, on this particular molecule, we only see double bonds. You might have a triple bond in the case of having a triple bond, like in the case of acetylene here. The first bond is a sigma bond, and then there would be two additional bonds. There's two pi bonds in there. Back to our butadiene molecule, though, there's a pi bond right there as well. And so we would simply say that there are two pi bonds on this molecule. The alternative version of this asked for what the number of sigma and pi bonds would be for C6H6. Now, technically, there's not enough information here to figure out what this structure should look like. A name like butadiene has a lot of complex information contained in the way that we structure that name. But means 4, di means 2, ene means double bonds, and then I can tell it's a hydrocarbon because of what the suffix is. But this alone shouldn't be enough for us. However, odds are what they meant was for us to have a benzene molecule here. There's not really anything else it could be based on that number of carbons and hydrogens. Again, pretty sure those are supposed to be two different problems. And this is the structure of benzene. So, same process applies here. In order to find the number of sigma bonds, I'm going to count everything that is the first bond between two nuclei. I think it's good to go systematically here, so I'm going to do all the carbon to hydrogen bonds first. 1, 2, 3, 4, 5, 6. Then I'll do my carbon to carbon bonds, kind of working my way around clockwise. So just the first of each of these bonds is going to count. So this is the 7th, 8th, 9th, 10th, 11th, and then, of course, 12th sigma bond. So there's 12 sigma bonds on that benzene molecule, and then to find the number of pi bonds, we're just looking for anywhere that we have a double bond. And so that's a double bond, that's a double bond, that's a double bond. Each one of those is going to give us an additional pi bond for a grand total of 3 pi bonds on my benzene molecule. Do I have any questions related to counting the number of sigma and pi bonds on these molecules? So far, so good? Excellent. Okay.
Sorry, hello,
Oh,
am I
hey.
hearable?
Yeah, I can hear you
Sorry,
now,
I
Garen.
didn't realize I was muted. Um, are we supposed to like know these,
No, you're not supposed to know these structures at all.
okay, yes, that's what I was gonna ask. Are we supposed to know these
Oh, you're
structures and
totally good. Yeah,
then
yeah, yeah.
count using
Really,
those?
what
Okay.
you'll see is just like in the homework, where like this is the last question you get asked on a Lewis dot structure problem. So something more
Okay.
reasonable would be like I give you like, oh, do the Lewis dot structure for CO2. And then you would go through, you would count the number of valence electrons, you would draw your structure, which I'm pretty sure you've done a few times by now. So hopefully you're starting to recognize CO2 looks a little bit like this. And once you have that Lewis dot structure, you can go through and apply the same approach. It's just that was a problem out of the textbook where they would have given you a picture to look at. I think it probably just didn't
Okay.
get copied over into the text form very well. And then you count the number of sigma and pi bonds by looking at the picture from the textbook. Here, we count them based on what we drew. So every first bond is going to be a sigma bond. Therefore, there are 2 sigma bonds. And then every subsequent bond, so this guy and that one, would be pi bonds. Those are going to be 2 pi bonds in total.
Okay.
Same approach, a little
I just wanted
simpler.
to make sure. I didn't think you'd expect us to know that, but I just
No, no.
wanted to make sure.
Don't worry. Someday, hopefully, you guys get there. But not today.
We'll see.
All right. Other questions related to counting sigma and pi bonds? Okay. Then we had another question in the chat from earlier. I'm going to go ahead and grab that. Win gave us this lovely Hess's law problem. So might as well drop that in the Hess's law section that I put here. Okay, so using Hess's law for carbon plus oxygen yielding carbon dioxide gives us a change in the enthalpy of that much. And then for CO plus 1/2 oxygen yields CO2 gives us that change. We want to find the change in H for, or the enthalpy for this. So I'm just going to go ahead and rewrite this quickly because it's a little bit scrambly in text format. We have the goal is to find the delta H for C plus O2 reacting to yield CO, carbon monoxide. And we were given 2 sample equations where we had C plus O2 reacting to yield CO2, and we had carbon monoxide plus 1/2 of an O2 reacting to yield CO2. The delta H or enthalpy for each of those was also included, and it's a necessary piece of information for us to calculate our new change in enthalpy. So for the delta H of that first equation, we got negative 393 kilojoules per mole. And similarly, down below, negative 283 kilojoules per mole. Okay, now these problems look intimidating. They got a bunch of weird symbols, it's a bunch of equations, but really what we're trying to do is kind of just like solve a puzzle. We're trying to see how we can stick together these 2 equations somehow in order to turn them into our desired equation. So the rules of the game are as follows. If you flip an equation around, you have to multiply your delta H by -1. If you change the quantity of one of your reagents or products, you have to multiply or divide your delta H by that same amount. And so all we're going to do is flip these guys around, add or subtract some number of, or not add or subtract, sorry, multiply or divide by some number of coefficients in order to create this top equation. So I'm noticing first that the carbon is on the reactant side here and on the reactant side there. Since we've got a carbon in both of those two places, I don't want to flip this top equation around. Um, I noticed that it goes on to produce carbon dioxide here, which is not listed anywhere in that top equation. But that's going to turn out okay in the end because notice that we have a CO2 down below. This CO2 is capable of canceling that top CO2 if we invert this equation. Just like when we were solving for our spectator ions, anything that appears on the reactant and product side, when we add equations together, kind of gets canceled out. And so I know based on the CO2 being here that I'm going to have to multiply this equation by -1. So I'm going to just redraw this now, where I have CO2 reacting to yield 1/2 O2 plus CO. This also solves a different problem for us. Notice that CO appears as a product in our goal equation, and it appears as a product now in equation number 2. I'm going to go through and check and see how things are canceling out so far. I see that we have. Is there a chance, Win, that something didn't copy over cleanly from one of these? Perhaps
I
for
just copied it straight from the website.
Okay, it does look like something went wrong though, because I'm noticing here that in our goal equation that it says O2 and there's not the correct number of oxygens on this other side. So what I'm going to go ahead and do is say it should probably have been 1/2 O2. Make an executive decision here that something didn't get copied over correctly, but that's no worries. So now what we can do is we're going to compare what we have on the reactants and product sides and see what cancels out. So our CO2 cancels with the CO2 over here because this is a product, this one's a reactant. I notice that I have 1/2 of O2 as a product here, but a full O2 as the product over there. We can cancel out a portion of our oxygen molecules. Of course, if we take 1 and we subtract 1/2 from it, we'll end up with 1/2. And so this 1/2 O2 completely goes away, and we end up with 1/2 of an oxygen molecule there. Now, when we go through and add everything together, we'll just bring down anything that hasn't been canceled. So we have carbon plus 1/2 of an O2 reacts to yield CO. And we want to check to make sure that this perfectly matches our goal equation, which it does. And so then the way this allows us to calculate our delta H for that process is we have to apply any of the changes that we made on our delta H for each of those partial processes, and then we add those two together. So here it was simply just turning this negative 283 into a positive 283. And so real quick, I'll do negative 393 plus 283 gives me, oh, that negative sign didn't apply, sorry. Negative, oh no, it's 393 negative plus 283 gives me negative 110 as the delta H for this process. Any questions on this guy? Okie dokie. And that's it for those questions in the chat. So I'm just going to start doing things systematically here, unless somebody has a particular problem they would like me to go through. So Everything here is just going to be a section from that study guide. These study guide sections were created by me looking at the exam and then saying they need to know this, they need to know this, they need to know this. And so following that study guide, grabbing problems from the various homework assignments related to them is going to help you to answer the test questions relatively quickly. We don't have quite as long as we did on the last one. Last one, I gave you a full 2 hours. This one, I'm pretty sure I have it set at 90 minutes. So it's still a good chunk of time because there's a lot of questions. I think I have it set at 19 questions, but very little math compared to what we were doing previously. So let's start with Lewis dot structures. To draw a Lewis dot structure, of course, we need a chemical formula first. Let's say we had something like, we'll start easy. We'll do something like PBr3. From that PBr3, the place I want to start is by finding the number of valence electrons that structure has. Valence electrons are the guide for how we get to build our molecule, how many bonds we need, how many lone pairs we need, etc. So you'll, of course, have a periodic table. I'm just going to use this one for today. I want to find each of the elements on the periodic table to figure out how many valence electrons they have. Now, phosphorus right here is in group 15, and some of you know a rule for calculating how many valence electrons it is based on it being group 15. I think that's silly because I know that all the noble gases have 8 valence electrons. So for me, it's always been fastest to just count backwards from 8. And so I go 8, 7, 6, 5. Phosphorus has 5 valence electrons. Similarly with bromine, start at krypton here, noble gas with its 8 valence electrons, and then each of those bromine atoms must have 7 valence electrons. So what I need to do now is I'll add up my valence electrons for this compound. I have 5 valence electrons for the phosphorus plus 3 times 7 for each of those bromines. 21 plus 5 gives me 26 electrons to spend. I like to keep a running tally on my valence electrons as I'm filling in my Lewis dot structure. The steps I'm going to do here are the way that I think it's the fastest to solve this type of problem. If you followed some other rigorous approach from a different resource and it works for you, fine, no problem. What I always like to do is start with my central atom. The central atom is usually going to be the first atom listed, or it's going to be the most electropositive atom. Electropositive is just the opposite of electronegative, so the thing that's furthest away from fluorine tends to be your central atom. Also, Gen Chem 1, spoiler alert, we tend to make one thing different than the other things, so it's pretty easy to tell what goes where. Phosphorus goes in the middle, and then I'm going to spread my bromines out around it. Now, where I put those bromines doesn't really matter for now. I'm just kind of putting them on cardinal directions there, so it's easy for me to space out my electrons while I'm drawing them in. Of course, this would not be a molecule if we didn't have at least one bond between each phosphorus and the bromine. And so once I have all of those there, my trick is I like to give the phosphorus or the central atom, whatever it may be, an octet of electrons first. So giving it an octet is going to vary based on how many atoms are around it. But in this case, since we had 3 bonds times 2 electrons, that's 6 electrons total. And then I add a lone pair to the phosphorus so that it has the octet. The logic here is that if I need to create a double bond later because one of my bromines turns out to be electron deficient, it's very easy for me to share them outwards from that central atom. So I have now spent 8 electrons. I will subtract that from my initial amount, so I have 18 electrons remaining. Electrons like to travel in pairs, so I'm going to start filling in pairs of electrons around my atoms that don't have an octet yet. So 2, 4, 6, 8, 10, 12, 14, 16, and that is 18 electrons spent. So I update my total here, and hey, look at that. I've got no electrons remaining in my bank. This is where we want to be. Looking at that structure, I notice that every one of my atoms has 8 electrons around it in total. And so this is a happy Lewis dot structure. Any questions?
You mentioned that you spent 8 electrons. Can you go back to that part?
Yep. The 8 electrons were the phosphorus and each of these bonds and lone pairs. So those are the first 8 I spent. Remember
Okay.
that every bond is 2 electrons and every lone
Electrons.
pair is 2 electrons.
Yeah. 2, 4, 6. Okay.
Any other
Got it.
questions?
So would this molecule have four domains?
It does have 4 domains, absolutely. So let's go ahead and finish out our VSEPR analysis of this guy. You might just be asked for a Lewis dot structure on the exam, although I didn't really put a way for you all to draw on the test. I know that like touchscreen, like point and click stuff can be pretty terrible. So all of the assessment is really going to be based on your ability to fill in properties of the Lewis dot structure, kind of like in the homework. So looking at this, we want to figure out all of the different VSEPR properties it might have. Let's start with determining the electron density areas around our central atom. So the number of electron density areas or domains or regions of electron density, it's a bunch of different words to describe it, but it all means the same thing. You want to count the number of places that you have electrons. So I see that we have a lone pair there. That's on one side by itself. Every bond or bonds between two unique atoms is going to be another domain or region of electron density. And so in this case, I have 4 domains. Or, of course, 4 regions of electron density.
So is the only thing important when it comes to domains the phosphorus, like the center atom? Is it anything important
We
when it comes to the
always
domains?
define our VSEPR theory around a specific atom because every one of the atoms on a molecule has 3 dimensionality and has its own sets of electrons that can point in any which direction. So, by definition, General Chemistry 1 course, we always say with reference to the central atom.
Okay. Just wanted to make sure.
Yeah. Good thing to clarify. Okay, let's identify the electronic geometry. So to figure out the electronic geometry, you would go ahead and take a look at your VSEPR table. Let me see if I can get that pulled up so you can see the exact one you're going to get. It's the same one that was from our homework, so hopefully it looks familiar to you. There it is. Okay, so this is the one you're going to have. I'm going to navigate to the region where I saw that I had 4 domains. Once I'm in that 4 domain region, notice that all of the electron geometry answers are the same for 4 domains. That's because the number of domains determines the electron geometry. VSEPR stands for valence shell electron pair repulsion, and so they adopt this tetrahedral arrangement because that's how many regions of electron density there are. Therefore, on your exam or homework or whatever you were working on, you would remark that this is tetrahedral. From there, distinguish between bonding and non-bonding. So you want to see any lone pairs or bonds between our atoms. The reason we want to do that is because looking at this chart, once again, we can figure out what the molecular shape should be based on the number of bonded atoms and lone pairs. So looking back at that structure, I noticed that we have a phosphorus with a lone pair of electrons right there, and then everything else is bonds. And so we have 3 bonded atoms and 1 lone pair. I'll try and match that for something inside of the 4 domains group. I see right here for AX3E, 3 bonded atoms, 1 lone pair. This tells us that our phosphorus tribromide should be a trigonal pyramid, and then we have a 3-dimensional representation of that drawn here. Notice that the lone pair of electrons is sticking up, and it kind of pushes each of those bonds to the bromines downwards here. So this is not a perfectly symmetrical molecule. We have all of those x's are kind of bowed downwards, forming the vertices of our triangular pyramid. So we've identified that it is trigonal pyramidal using VSEPR theory. We can estimate the bond angles around the central atom just as easily. We need to take a look at our chart once again. Notice that the bonding angle is spelled out for you right there. Should be 109.5, and that's a consequence of it having a tetrahedral electron geometry. Same thing applies for the hybridization. Just says it literally right there. So our hybridization and bond angles, the angle is equal to 109.5, and the hybridization is SP cubed. Now, for polarity, this is a topic that can be confusing for some students. It's a little bit challenging to think in 3 dimensions, but it helps to have a good Lewis dot structure down first and then look at that VSEPR table to kind of get a better idea what the 3-dimensional structure should look like. We're going to determine if individual bonds are polar first. To determine the net polarity of our molecule, we have to know if the bonds are polar or not. If they're not polar, then it can't be a polar molecule. In the case of PBr3, I'm just going to redraw it here for clarity with a little attempt at drawing the 3-dimensionality. So the dashed line is supposed to represent a bromine going away from us. The shaded in wedge is supposed to represent a bromine coming at us. And then the straight line is something that is perfectly in the plane of the page. Each of these bonds is polarized, probably towards the bromine. I don't know exactly off the top of my head, but bromine is a halogen, and halogens tend to be pretty electronegative. At the very least, I know it's not exactly the same as whatever phosphorus's electronegativity is. So I use these arrows to represent that the electrons are being pulled towards those more electronegative bromine atoms. And then the little slash through the tail means that other end is more positive. So looking at this structure, it seems like the net dipole moment for this molecule is going to be pointed downwards like this. The reason is because we add all of these vectors together and we see that there is no component that's pointing up at all. That just does not happen. Instead, we see that they're all kind of fighting with each other, pulling in these different angles, kind of down and away. And so overall, there is a downward pull on that phosphorus. Therefore, I would say this is a polar molecule. So in order to determine the polarity, it's a multi-step approach. You have to first draw the Lewis dot structure. You have to determine what its VSEPR structure should look like, determine the polarity of the bonds, and then decide if they cancel each other out perfectly or not. In this case, they do not cancel out perfectly, therefore PBr3 is polar. Any questions? Cool.
In the homework, I think there was a subsequent question about pi bond.
Sure. The number of pi bonds is just about looking at the number of double bonds and triple bonds that there are. In this molecule, there are no double or triple bonds. Therefore, the answer would be 0 pi bonds.
0. Okay.
Other questions on this one? All right, we spent quite a bit of time on Lewis dot structures, so I'm going to fast forward to some of the more mathy stuff, and we can revisit these at the end of the review session if we find time for it, and if there is a desire to do that. So, the mathier stuff from this exam is going to be related to thermodynamics. In particular, we're going to have some calorimetry problems. I've collected two of them here. There's essentially two flavors of calorimetry we're going to encounter. There's going to be the type where it is just a single calorimetry equation, where you are figuring out either the specific heat capacity of a compound or the temperature change or the mass of it. And then there's also going to be the calorimeter type of problem, where you have to set two equations equal to each other. Essentially, the heat out of one thing is equal to the negative heat into the other thing. So let's go ahead and do the first type first. We want to calculate the final temperature of a system where we have a 50-gram sample of water at 100 degrees Celsius and a 100-gram sample initially at 14.1 degrees Celsius are mixed together. Actually, I think I got two versions of the calorimetry one. Sorry. This is more complicated than I meant for it to be. I'll just come up with a different one. Let's say we have a 200-gram sample of iron is heated to or from 14 Celsius to 44 Celsius. Its specific heat capacity is something small because it's a metal, 0.7. Why not? That's not the exact heat capacity for iron, but it's good enough for now. And that, of course, is in joules per gram Celsius. How much heat did the iron absorb? So, to solve a problem like this, you of course need your calorimetry equation. I gave it to you here in the review. Might not be that kind on the exam. Make sure you do commit this one to memory, where the heat is equal to the mass times the specific heat times the change in temperature. Also important to remember that change in temperature is equal to T final minus T initial. So for this particular problem, I'm looking for Q, the heat that the iron absorbed. That's going to be equal to the mass of iron, which is 200 grams, times my specific heat capacity, 0.7 joules per gram Celsius, and then times the change in temperature. Now, my change in temperature, it's important to be able to recognize which one of these is initial and which one is final. If it says from something to something else, the from is the initial, the to is the final. So I'll put 44 Celsius minus 14 Celsius. And that should be everything I need to solve here. Notice that the grams is going to cancel and the Celsius is going to cancel, leaving us just with joules, which is exactly what I wanted to find. Just because some people like to look at numbers, we'll take 200 times 0.7, and then 44 minus 14 is 30, so times 30. Gives me 4,200 joules as my value for Q. So that's the easy version. Any questions on the easy version? Okay. Slightly more challenging than that is going to be when you're using an actual calorimeter for these problems. Now, a calorimeter is a device that's supposed to prevent exchange of heat energy with its surroundings. And so what that means is that we can assume that negative Q, the heat leaving a system, is going to enter the calorimeter and it'll become positive Q. Remember that heat is a signed quality, and so you can have heat enter a system, which would be a positive value for an endothermic quality, or you can have heat leaving a system, which would be exothermic and have a negative value. So because we have the calculation, or sorry, we have the equation for Q up above, I can rewrite this as the negative mass 1 of something times the specific heat capacity 1 for that thing times the change in temperature, and I actually like to expand the change in temperature term here right away. I like to say T final minus T initial 1. The reason I label it as T initial 1 is because we're going to have two different initial temperatures, but we're only going to have a single final temperature. That is, by definition, how a calorimeter works. You put a hot thing in a colder thing and you wait until thermodynamic equilibrium is established. At that equilibrium point, you should have the exact same temperature for both the container and for the object you added to it. So, that's why I like to expand this term when I'm writing this out. And that's going to be set equal to M2C2 times T final. Notice T final is the same once again for both sides, minus T initial 2. And now this is going to be a different value for sure. Otherwise, it's going to not tell us very much about the calorimeter when we solve it. For those of you worrying about which side the negative sign goes on, good news, it does not matter. You randomly pick a side, make that side negative, and then because of the way algebra works out, it resolves itself in the end. Remember that I could multiply both of these Q values by -1, and algebraically, that means it's the exact same value. And so even if I labeled these as Q1 and Q2, it ends up becoming positive Q1 is equal to negative Q2. So that's the proof for saying don't stress about the negative, just make sure something is negative. Okay. Now that we've got this set up, all we have to do is plug different values in. So I'm going to say that my -1 is going to be the metal. Make sure you don't get those confused as you're solving. Negative mass of metal 1 is going to be at 25 grams times the specific heat capacity of that metal. Searching, searching, searching. I don't see the specific heat capacity of the metal listed anywhere, which kind of makes sense because we called it an unknown metal. So I'm actually looking for my specific heat capacity for that metal here. I'm just going to leave it labeled as C1. Times TF, the final temperature, remember, is the same for both the system and the calorimeter. And so looking around, it seems like the final temperature becomes 20.15. So 20.15 Celsius minus the initial temperature. We know that it is 99 degrees Celsius for that metal. And that's everything that we can fill in on that side of the equation. So we set that equal to the mass of the water. We had 50 grams of water times the specific heat capacity of water. It isn't listed here. I'll double check to make sure I listed it on your exam. I don't expect you to memorize it, but it is 4.184 joules per gram Celsius. I feel like we've done so many of those problems that you guys have accidentally probably memorized it. If not, like I said, I will include it on your exam. So 4.184 joules per gram Celsius is the specific heat capacity of water. And now I'm multiplying that by my final temperature, again, same for both sides, minus the initial temperature of the water, 5.64 Celsius. From there, you just need to rearrange and solve. I guess I'll do that. So I'm going to simplify the terms in parentheses first. I think it's a really good place to start. Make sure when you're doing your work for these that you're as specific as possible, show as many steps as possible, because if you do make a small mistake in your calculation, the exam's going to mark you wrong. But remember, I go back and I fix those things when I look at your work later. I think most of us have gotten quite a bit of partial credit from me going back and double checking things. So make sure that I can read what's happening and understand it. So the term in the first parentheses simplifies to negative 78.85 times C1 times 25. And then that's all negative. And on the other side, 50 times 4.184 4. I'm just dropping the units here for simplicity's sake, because I know that they all cancel out in the end anyway. So here, 20.15 minus 5.64 gives me 14.51. I can multiply all those values together. That'll simplify things a little bit over there. 50 times 4.184 times 14.51. That's going to give me 30. Ooh, there you are. 3035.492. We'll take care of the sig figs at the end. And then for the other side here, we're going to take 25 negative times the 78.85 negative. And so I expect that that side should turn into a positive value now. And we get 1971.25. C1 is what I'm calling my variable there.
Quick question.
Go ahead.
Sorry. But doesn't that negative sign also affect the negative 78.85? So
It
wouldn't it
did,
end up?
yes. So
Yeah.
the negative 25 C1 times negative 78 becomes a positive 1971.25.
Yes, but I'm sorry, I might just be really confused, but isn't the negative 78.85 also inside the parentheses affected by the negative sign? So wouldn't this be a
Yes,
double negative?
yes, so it's positive. Negative times a negative is positive.
Yes. But
Yes. And I wrote it as positive.
yeah. I know that's what you're saying, but I'm sorry. The negative 25 C1 becomes negative, and the negative 78.85 becomes positive, and then they multiply together and you get a
No,
negative.
that's not how that works. You are just a little bit confused there. I'm sorry. These are not separate terms. This is 25 times C1 times negative 78.85. And so I could resolve the stuff inside the parentheses here first,
Oh,
and it
yes.
becomes
Okay.
negative whatever,
Yeah.
and then times the negative 1. No
Sorry.
problem. I did probably confuse things a little bit by leaving it in parentheses there. You could just as easily think about it like this. If I take those parentheses out and I put a multiplication symbol between each of these, I think it probably makes more sense now, right?
Yes, sir.
Awesome. Okay. Glad we could fix that. Um, okay, so we got the positive value on both sides. And then to finish it off, I'm just going to divide to isolate my specific heat capacity for the metal. So 1971.25 on both sides. And that'll give me a number. So we'll take the 3035.492 divided by 19.71.25. Wait, I did something wrong there. Hang on. 1971.25. And we got 1.53. So C1 is equal to 1.53. Some quick checks you can do to make sure that you got a reasonable value here. Specific heat capacities tend to be on the small side. The largest specific heat capacity I've ever seen was for like helium, and I think it's like 6 or something like that. Most of them, especially for metals, tend to be in the like 1 to like zero point 0.5 range. This is kind of high for a metal, but it's just a random problem, so that's probably why. You shouldn't have specific heat capacities that are larger than 10. That would definitely be incorrect. Also, specific heat capacities by definition have to be positive values. Otherwise, it would imply that energy was spontaneously flowing out of this thing, making it hotter. That's not really how the universe works, unfortunately. And so if you end up with a negative value for your specific heat capacity, you've definitely done something wrong. Same thing applies for the masses in a problem like this. If you get a negative value for your mass, you've definitely done something wrong. CERN may be cranking out antimatter now and trucking it around. That was a big headline last week, is that they shipped like 100 atoms of antimatter from one side of the facility to the other. Good for them. This is a chemistry class, not a physics one. We don't believe in antimatter here. You have to have positive values for all your matter. Other questions on calorimetry? Okay. Let's do a couple of electron configuration problems. I think some of you are probably doing electron configurations the hard way. I want to show you the easy way to do them. So, the periodic table, boy, it's shaped weird, isn't it? Why didn't they just put things in a straight line? Are they stupid? Well, it turns out there is some logic to how we've organized this thing. The reason it's set up in these weird blocky arrangements is because those blocks correspond to the electron configurations of the elements that fill those columns. So, by understanding which electron configurations apply where, you can very easily look at an electron configuration and work to figuring out the atom without needing to count, 118 spaces on the periodic table. For groups 1 and 2, these are where you are adding s electrons to your atom. So the highest energy electron you've added to beryllium is the 2s2 electron. Across this big gap here, this area are where we're adding p electrons to our atoms. The middle section here, this is where the d electrons fill in, and then the cutout section down below, that's where we stick f electrons as the highest energy valence electrons added. Therefore, we can refer to each of these different rectangles of our periodic table as the corresponding blocks. We call this the S block. These are the P block. This is the D block. These are the F block. Understanding that allows you to very quickly determine what your electron configuration is describing without ever having to count electrons. Let me show you what I mean. We'll pop back over here and say what element has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p1. Now, I'm sure you guys have done the slow way of this before. You add up each of these little values, pray you didn't get any of it wrong, and then you go and count that number of spaces. Easier way to do it, that 3 for p electrons specifically means third row of the periodic table. That's always the case for the s and the p electrons. The exceptions are for d electrons, they start 1 row less, and for the f electrons, it is 2 rows less. So, for example, you might remember that our first d electrons are for 3d, and so that happens with scandium is the first d electron we add. It is 3d1, and it happens to live in the 4th row of the periodic table. Similarly, for the f electrons, the first f electrons we fill in are 4f. So we would start adding 4f electrons in the 6th row of the periodic table. So, looking back, we see 3p1. So I'm going to zoom in on the 3rd row of the periodic table. And then that P1 tells me inside the P block, I count 1 space over from left to right. Therefore, 3P1. This must be aluminum. You can always go ahead and check your work, right? Let's do that now. We would check our work by adding up the total number of electrons. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 1 is 13. And then I do notice that aluminum has atomic number 13, so that is the correct electron configuration for aluminum. But learning it this other way is just a much quicker approach. Aluminum was a relatively small element, but if I told you that I had a, let's say, radon, I'm actually going to do that one. We'll say we have radon, so Rn, 7s2, 5f 14, 6d4. You would have to look at radon, figure out its atomic number is that many electrons, and then you add all those together, and then you count that many spaces. What a pain in the butt. Instead, I'm just going to pay attention to 6d4. I look at the periodic table. I see for the 6d electrons, remember, they fill in one row late, and so that's in the 7th row of the periodic table. And I count 4 spaces over. So it's a 1, 2, 3, 4. Marcus should be Seaborgium here. Sorry, some periodic tables are a little bit weird about how they space these out. Sometimes it's easier to look at it in wide format. We can more easily see what I'm talking about here. So yeah, technically, lutetium and lawrencium are d electrons here. So we'd count 1, 2, 3, 4. Seaborgium is the element I'm describing with that electron configuration. I just counted 1, 2, 3, 4 in that 6d block. Okay, back to a more reasonable example though. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1. I'm going to zero in on that 3d1. As I just mentioned a little bit ago, and we'll switch back to the classic view, the d electrons start with 3d, and so 3d1 would be describing scandium here. There you have it. You can use this same approach working backwards. So if I wanted to find the electron configuration for germanium, what I would do is I would say, okay, germanium is in the p block. It's 2 spaces over in the p block, and so it is 4p2 electrons there. And then you just fill in everything else moving backwards from that all the way up to maximum capacity. The maximum capacity of the orbitals is very easy to figure out just by looking at the number of elements in each block. So if you forgot how many electrons go in the d orbital, you would count the number of spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since there's 10 elements in the d block, there must be 10 electrons in a d orbital. So to finish that one out, I was talking about the electron configuration for germanium. We'll call it GE. And then I'm just going to fill in all of the electrons up to that 4p2 that I know is the last electron added to germanium. 1s2, 2s2, 2p6, 3s2, 3p6, 4. Sorry, got a little messy there. 3p6, 4s2, 3d10, and then 4p2. That's my approach. Again, if you have been doing it differently and it works well for you, you may continue to do it that way. You won't receive any penalty. Any questions on electron configurations?
Can you write the electron configuration for iron with a 3+ charge?
Sure. So charges add a little bit of a complication to the mix. When you have a charged species, be it a cation or an anion, you have to modify the number of electrons. Remember that electrons are negative. Therefore, if you have a negative charge, you would expect that you have more electrons in your electron configuration. Here, iron 3 plus means that we have lost 3 electrons from that electron configuration. So looking at iron here, if we remove 3 electrons from it, it goes from here to, that's 1 electron removed, 2 electrons removed, 3 electrons removed. I would anticipate it would have something close to the electron configuration of vanadium. Now, I'm assuming you chose that specific one because you saw it somewhere and it surprised you, right?
Yes, since you have to like take electrons from the
Yeah.
4 group
It
first.
does get a little bit tricky there. The reason is because if you look at the actual way that the orbitals fill, so this would be the 4s2, and then the 3d10 is just a little bit higher in energy than that. As a result, there can be some mixing of these orbitals where like electrons will jump back and forth whenever it's convenient for them. And so to start filling it in, it would look like this. We fill in the 4s2, and then iron is the 1, 2, 3, 4, 5, sixth one in the D block. So I would put 6 electrons into that configuration. 1, 2, 3, 4, 5, 6. There's a general rule you can follow where we prefer to have full orbitals, half full orbitals, or empty orbitals. That's just a good general rule for trying to predict why some of this weirdness happens where things don't fill in exactly according to the Aufbau principle. So here, I'm anticipating we'll remove this electron first because it's the only paired one in that 3d10 orbital. Or 3D, not 3d10, sorry. So we're going to take that guy away. So that takes us to iron +1. Then, since this is a half full orbital, that's preferable. We don't want to break that half full orbital. So I'll take this one away as the second electron I remove. Now we have 2 half full orbitals. This is a good situation, but we've only removed 2 of our 3 electrons total. I have to decide where I want to take that third electron away from. Since these are very close in energy, and since the 3D is receiving a lot of stabilization from having 5 electrons that are all half full orbitals, and since an empty orbital is just as good as a half full one, I'm actually going to remove the 4s electron here as my third one. So this is probably the result you found, right, Win?
Yes.
Great. So this is rationalized by saying that you want to have half full orbitals whenever possible, full orbitals or empty orbitals. Those are all preferable. So the s electrons are really happy with whatever, right? They started full, they were happy. Then they became half full, they were happy. And then they became empty, still happy. I am not quite this sadistic. I am sadistic, but not this sadistic. I'm not going to give you guys a question like this for an online exam.
So we won't have to know how to, I wouldn't call this graph, but write in questions like this.
There won't be any write-ins where you have to do the electron configurations.
Okay.
Yeah. Other questions? Okay. Then we briefly discussed the quantum number n earlier. N is the shell number. It basically just corresponds to the row of the periodic table, except when you have the d and f electrons. For the d electrons, it's n-1 is where you start filling those in, and for the f electrons, it's n-2. The other number that I want you to know, the other quantum number is called L, or angular momentum quantum number, and it corresponds to the shapes of the orbitals. Really, it's just about whether you know it or not, and so I'm just going to map that out for you very briefly here. So when L is equal to 0, we say that's an s orbital. And we usually use a cursive L, but my touchscreen is terrible here. Let me try again. L is equal to 0. That's an s orbital. When L is equal to 1, it's p. L of 2 is d, and L of 3 is f. So one of the questions that I asked some of you on that oral quiz would be, for an L of 1, which element could it be? Something like that, right? On your exam, I think I asked a question like, what is the L value of the highest valence energy electron of this element? Something to that effect. So if I said that for an L of, let's say for L of 1, actually, I'll combine both problems. So for an N of 3 and L of 1, which elements, valence electron, could these describe? So you want to find a situation where n is equal to 3 and L is equal to 1, and then pick an element from the periodic table where that happens. Remember, N is the row, so I kind of triangulate down to the third row here, and then I'm going to scoot past these two. I know those can't apply because when L is 1, we're in the P block of the periodic table. And so a good answer to this question would be any of these 6 elements might be described by an N of 3 and an L of 1. Questions there? For periodic trends, this is kind of a know it or you don't situation. I would recommend going back into your textbook, maybe like annotate a periodic table, not the one that you're actually going to bring to the exam. Remember, that has to be blank. But just like to practice, and while you're reviewing, it might help to have an annotated one that you're looking at. Ionization energy, to figure out ionization energy, for the most part, what you're thinking of is how badly does this element want to hang on to its electrons? You can kind of orient yourself based off of the noble gases. Noble gases are the goal for all of our elements. Once you've reached noble gas electron configuration, those electrons are considered core electrons. They are considerably more stable. And so if it gets you closer to a noble gas configuration, if you lose electrons, it should be relatively easy. If you're getting further from a noble gas configuration by losing electrons, ionization energy should be relatively high. So let's try to predict which of 3 elements would have the highest first ionization energy. Looking at a periodic table, let's say, do we expect bromine, iodine, or selenium to have a highest first ionization energy? The other trend with ionization energy, since we're dealing with actually stripping electrons off of atoms, as we get further and further and further from the nucleus, we expect that the nucleus's pull becomes weaker and weaker. It's not unlike, Earth's gravity. When you get far enough away from Earth, things aren't influenced by our gravity anymore. So when you get really far out for the super big elements, kind of like iodine, I would anticipate that first ionization energies go down considerably. That's because those electrons are barely held by the iodine when they're way out in the stratosphere like that. So we can rule iodine out. Now we're comparing bromine and selenium here. Selenium is closer to being a noble gas moving in this direction than the bromine is. Remember, first ionization energies, we are only removing electrons, so we're moving the electron configurations in this direction. Bromine being really close to krypton, it doesn't want to lose electrons at all, it would much rather gain them. So I would anticipate that bromine has the highest first ionization energy of these 3. You might be asked a similar question to that on your exam, or you have to compare their proximity to the noble gases and then their row number to figure out which has the lowest or highest first ionization energy. Electron affinity is very similar to ionization energy in terms of its general trend, but we actually do look at adding electrons to the different elements, and so we have to look at the state of fullness that their orbitals are in. Remember, I just said a couple of problems ago that having a full, half full, or empty orbital is preferable. You might encounter a situation where you're comparing the electron affinity of something like magnesium to the electron affinity of something like sodium. I would actually anticipate that sodium has the lower or more negative electron affinity than magnesium, because magnesium already has a full orbital. Adding an electron to the magnesium, it has to get stuck into the 3p1 orbital, which is not full, it's not empty, it's not half full. So that 3p1 electron really didn't want to get stuffed in there. On the contrary, sodium had 3s1. Adding an electron to it gives it the full orbital 3s2. So, comparing 2 elements like that, we would say that magnesium had the more positive or less favorable electron affinity. Most of you all were pretty good with some of the other periodic trends. We talked about electronegativity. That's an essential one. I don't expect that you guys memorize any electronegativity values. Just know that the closer you are to fluorine, the higher your electronegativity is. This is pretty basic math. I do want you to know this formula, know this relationship. The speed of light is equal to the wavelength, lambda, times the frequency, which looks like a V, but it's technically the Greek letter nu. Um, Wavelength and frequency are inversely related to each other. As the wavelength increases, the frequency decreases. As the frequency increases, the wavelength decreases. Um, Frequency and energy are directly proportional to each other. Waves that have the highest frequency have the highest amount of energy. The way that I've always demonstrated this for my in-person students is it takes relatively little energy for me to mimic a wave like this, right? But if I want to mimic a really fast wave, it takes quite a bit of energy for me to do it. So you can rationalize it that the high frequency wave took more energy for me to demonstrate. And then this is just one of those look at the chart things. And so that's actually the end of the study guide then. Some of those are concepts that are not particularly good for me to demonstrate problems for. I'm sorry about that. You'll just have to do some reading on your own, make sure you're up to date on the definitions and the behavior of those different things. I'll open the floor back up for questions, though, before we conclude tonight. Is there anything else that you all would like to have touched on? Anything you're still foggy about? We can spend a few minutes at the end here going over that.
Just real quick, while people are asking questions, can you get back up to the formula with the speed of light? I didn't write it all the way down, and I wanted to
Sure.
get that. Thank you.
Yeah, this is also copy pasted from the study guide. It doesn't hurt to reinforce things, right? Other topics, other questions, anything else you guys want to cover?
So I have one question.
Okay.
For electronegativity, noble gases, those technically aren't like applicable, right? Because those aren't electronegative.
We can assume, for the purposes of this online general chemistry course, yeah, you can ignore electronegativity of the noble gases. We can assume, for the most part, they don't react, and therefore they shouldn't really have an electronegativity that matters. They do have one, and it's weird, and we don't worry about it.
Okay, thank you.
Yeah, of course.
From the formula, it says speed of light equals to wavelength times velocity, and the symbol is V.
No, it says frequency,
Oh, okay.
and the symbol is nu, but nu looks a lot like a kind of italicized V.
Okay.
Anything else, guys?
I just have a general question. I know you post this stuff on YouTube. Will this be on YouTube like before tomorrow or like by tomorrow kind of thing? I like
I
to watch
will
the
I will
videos and
do
see how
my
you solve
best.
things.
Yeah. So it does take like a
Um,
usually like half an hour or so for my computer to compile it. And I'll try to get it uploaded tonight.
okay, yeah, yeah. I mean, it's no problem. I like watching how you solve it. That's what
Absolutely.
helps me figure it out.
Yeah.
So,
Glad to hear it.
yeah.
Um, can you share your YouTube link in the chat? I don't have it.
I think it's just right on the front page of our Canvas
Yeah,
course.
it's on the home screen.
Yeah, if you
When you
click
hit home, I
home
think it's one of
and
the
then
first up.
scroll down, you'll see Dr. Ayad's YouTube channel is the very last thing listed.
Okay, thank you.
Yeah. And you'll find old reviews there and stuff, and the problems that I work for those exams are kind of the same as for this one. You'll just find like slightly different material.
Got it.
Sorry, one last general question.
Sure.
Will we be doing one of these for the final exam as well?
Um, yeah, yeah, I think I can do that for you guys if you think
Okay.
it'd be helpful.
Absolutely.
All right. Well, so it shall be then. Okay. Well, If there isn't anything else, thank you so much, you guys, for attending. I really appreciate it. I know that like burnout is pretty real towards the end of the semester, and your classmates couldn't make it tonight, but I really do appreciate you guys being here and keeping me company because otherwise I'm just yelling about chemistry at a computer screen all night. Which is still fun, but it's different. Thank you very much for being here. Hope you guys found something useful. Let me know if you do come up with any other questions. Shoot me an email, schedule time to meet one-on-one. I'll do anything that you guys need to make sure you do well on this exam, all right? Take
All
care.
right. Thank you. Have a good night.
You too.
Thank you. Have a great day.
Take care, guys.
You too.
Thank you.
Yep. Have a good one.